Okay, there's something very important for you to note. If you go to the course wiki, okay, you know how to get there. And then go to the tab under dates and grades. Okay, if you go there, oh, sorry, I don't have an internet connection now, do I? So let me just turn it on. Yeah, so sorry, bear with me. If you go there, there's a special section that was just updated yesterday. I would like you to look at. Okay. Okay. Yeah, bear with me a few seconds here. Okay. Okay, if you go to the course wiki and under dates and grades, you will see there is a section towards the bottom. It's called letter grades. So look at this section more carefully. That's basically tells you about how your final grade is going to be calculated. Okay, just look at that. If you got any question about it, speak to me offline and I'll explain to you. Okay, I just wouldn't waste time in the class. But look at that section there. So it might be different from how your other courses calculated your final grades. Might be different. Oh, look at that. Okay. So today the plan, I would like to finish off the review on inheritance because starting from next week, we'd like to talk about more design patterns, which is more interesting. But before that, we have to make sure you got a foundation for understanding those patterns, which will be inheritance, polymorphism, dynamic binding, etc. Okay, this is where we left off from last time, right? We talk about this particular exercise of testing the post condition of your class, right? Do the exercise there and make sure you're comfortable with it. And so we'll start from today by saying, typically for your inheritance hierarchy, you may not just have one single level. So the example that we talked about so far, we got students under which we got resident student, we got non-resident students, right? Just two levels. But in general, you can have as many levels as necessary that's demanded by your projects. This is just one example. You can have domestic versus foreign, under which you got domestic, resident, domestic non-resident, etc. Okay? For your lab number 4, if you read through the description there, there's no indication about how hierarchical your entities or your movable objects should be organized. But there might be something you want to consider. Okay? How you actually design those entities will be completely up to you. Okay? But we can speak about it during my office hour. This is going to be some working example which is more sophisticated than the student management system that we talked about last time. Okay? I'm gonna go over that with you. In case you haven't got a handout, which I gave out last time, there's some spare copy at the front you can pick up. Okay? Let me just go over the hierarchy very quickly. We're going to use that when we talk about polymorphism, dynamic binding, expectation, casting, etc. So that's quite important. Let's take a look at the classes that we should pay attention to. Let's say we got a hierarchy for smartphones, okay? Because you simply got different kinds of smartphones, and each kind actually support different features. There might be some feature that's common. Also, there might be some feature that are unique for a particular kind. So that's something we want to look at. Let's say the following, okay? Let's say at the top we got a class called smartphone. Every smartphone we assume is going to support dial and also surf web. How exactly they do it is completely up to the subclasses, which we'll see. And under smartphone, we got two classes over there, two categories. Either iOS or it's Android, let's say. In the case of iOS, we're going to redefine the surf web. Let's say we redefine it by using maybe Safari, the web browser. And then for Android, let's say we redefine the surf web using Firefox, just different way of implementing it. And then let's say in the iOS, we got some new feature here called FaceTime, which is only available to iOS phones, but not Android, right? And notice that FaceTime is also not available in the smartphone, right? It's a unique feature that's only introduced at the subclass level. And also we got something specific to Android, let's call it Skype by default, okay? Let's say. And then under iOS and Android, we got even more classes to consider. Let's say under iOS, we got either iPhone XS Max and also iPhone 11 Pro. Specifically, let's say we have a feature in this class over here called Quick Take. Not too sure about what exactly that means, maybe to take the picture more quickly. It's a new feature, okay, that's only available to that phone. And then under Android, you got other phones. Let me just go over them very quickly so you will understand them. Let's say we got either Huawei or we got Samsung, right? For Samsung, you got a unique feature called side sync, okay? Under Samsung, you also got two models over here, right? Just as an example. And also under Huawei over here, you got either this model or this model. And for this model, particularly this feature called zoomage, I think something to do with AI when you take your pictures or movies. Anyway, it's just a unique feature, right? So that could be one example hierarchy you may want to think about for your lab number 4. Of course, it wouldn't be smartphones anymore, but instead, maybe actors or entities, right? But I'm going to use this as a working example for today when we talk about different concepts. And we may also have to review student management system again. So we got two hierarchies to consider. Let's now go over very quickly some terminology, which you may have known already from 2030. But let's go quickly. Okay? We talk about data type. So now when we say data type, it's a set of related runtime values. Specifically, when you talk about a class type, that means all the objects you can instantiate from that particular class. So like a reference, okay? References. And then every time you want to use inheritance to create some hierarchy, so different hierarchy might be possible. And we want to say the root is simply just any, right? We talked about last time. You can think about any class is like objects in Java. Implicitly, every class inherits from any. Okay, that one's easy to understand. Now, we want to be very careful when we say inherits, because it does suggest something that we have that's very important, inferential, when we talk about all the examples today. Okay, inherits. It's transitive in the following sense. Okay, I'm sure you can easily to imagine, but let me just be precise here. Let's say we have class A, and also we have class B, and also we have class C. Okay? You can think about every inherits relation here. You would say B inherits A, or like an extends A in Java sense. Also C inherits B. Implicitly, you can say because B inherits A and C inherits B, we can say implicitly C also inherits A. So that's what we said by transitive, right? Okay. So if you say, for example, C less than B and also B less than A, you know that C less than A, right? Transitive. Okay. You learned it in the basic math. What's so important about this is based on the inherits relationship, you would know which class in the hierarchy got more expectation you have in the compile time. That's really important information for us to decide behavior. But we'll see that a little bit later. Okay? And let me introduce very quickly terminology here, quickly. Let's say we talk about C specifically. Okay? Sorry, B specifically. With respect to B, B inherits from A. So in that case, we'll say A is the parents, right? And also C is a child class of B. But now we want to make it more general by saying rather than just parents, because there might be multiple levels in your hierarchy, we want to talk about something called ancestor, which is more general than parents. Also, we're going to talk about descendants, which is more general than child. Right? Let's see exactly how to visualize that. It's quite straightforward, but let's go over the slides quickly. Ancestor versus descendants, right? We're going to use ancestor and descendants very often for the rest of the lecture. Let's introduce them properly. Okay? What would be the ancestor classes for a particular class, let's say A? It would be A itself. Always remember, a class is its ancestor at the same time, just for our definition. In A's parents, A's parents' parents, A's parents' parents' parents, all the way up to the root of the hierarchy. Okay? For example, you can see that over here, this tree, right? I show you very briefly on Monday, this diagram here. This diagram is very important for you to really understand inheritance hierarchy in a general sense. Any inheritance hierarchy you might create for your projects will conform to such structure, right? Let's see very quickly. Let's say this. Let's talk about the reference point is class A. Let's talk about ancestor. So let me use, let's say, the blue one to say that's ancestor, okay? So what would be the ancestor for A? As I said before, it's going to be A itself, and also parents of A, the parents of A, all the way up to the root of the hierarchy. So that's the ancestor, the blue one. Okay. Any questions? Okay? And let's go downwards as well. There's another concept called descendants over here. So descendants. Of course, it can be plural. And for descendants, let me use maybe orange to say, okay? It will be, first of all, children of A. Oh, also A itself is also its own descendants. So a class is both at the same time, its ancestor and descendants for our definition, okay, at the same time. So the ancestor for A includes A itself and its children, and also its children's children, its children's children's children, etc., all the way down to the leaves of the tree. So it's going to include basically all the subtrees below A. Okay, so you can see we got two categories of classes in the hierarchy where we chose A to be the reference point. Okay, guys, any questions? Okay, right? Remember last time we talked about expectation, right? Expectation now is very important to visualize. We talked about expectation last time. When I actually declare my attribute, let's say maybe objects over here of type A, I know that basically the expectation I can have on objects at the compile time would be all the features that are inherited to A, which could be maybe there's some new feature that's introduced at the A level, or it could be some feature that's in A's parents. There might be some other feature in A's parents' parents, and all the way to the root. So you can see all the features that's defined along the ancestor path of A's, along A. They will be inherited to A. So they form the expectation for A. I'll give you an example in just a moment. Okay. So now, and also you can see this guy over here, whatever that's defining A, the new one, right? They will also be inherited to all the descendants of A, and etc. So it's really about accumulation. Okay. Let's say this. Before I go to another illustration, if I arbitrarily pick two classes, let's say I pick, let me use a different color to show you. Let's say I pick this class over here. I'll say this is class 1, okay? And then I pick another class over here along the tree. Let me call that class 2. Right? You can see class 1 here and class 2 here. So we got C1 and C2. Can you tell me which class at the compile time has more expectation? When I say more expectation, I meant the more features you can call upon attributes of variables of type C1 or C2, and then the more expectation they are, right? C1 or C2, which one has more expectation? C1, C2? C2, right? Because it's strictly lower in the hierarchy. Okay, that's something you have to know, okay? C2 over here has more expectation, or wider expectation, doesn't matter how you say it, right? Either say more expectation, or you can say wider, just wider, like a larger set. Expectations than C1, because it's lower in the hierarchy, right? This kind of visualization is very important when you actually consider inheritance hierarchy. Jordan, question?
So, I was wondering, because like when we make a feature that has like a bunch of preconditions and postconditions, does the fact that those features can be overridden?
So you're talking about contracts specifically, right?
Yes.
Okay. Jordan's question is really important, but let me just answer it very briefly because we're going to cover that in detail in a later lecture. Jordan's question goes like this. So what we're talking about here is just about what features you may call for a particular class, right? On the other hand, Jordan's question was like this. Since a very important learning outcome for this course is to learn about contracts, like a precondition, postcondition, class invariance. Let me just make it a little bit more simplified. If I have class A over here being the ancestor, and then I have another class over here called B. In class A, if I have feature F, also in class B, I also have feature F, right? And then if I have require for precondition something here, and also I have ensure also something here. So now, if I also have require, also I have ensure. Let me make it a little bit more precise for you, okay? So here, let's say requires, it's going to be some Boolean condition, okay? I'll just say precondition number 1, okay? So this will be precondition number 2. And this will be postcondition number 1, and this will be postcondition number 2. Jordan's question really is, if I try to call this version of the feature f at the runtime, dynamic binding is going to make sure if my dynamic type is actually b, it will make sure I call this version of f. Now the question is, at a runtime, what will be checked? For example, for sure, it seems to you, precondition number 2 must be checked, right? It's a precondition. But what about precondition number 1? Remember I said last time, contracts will also be inherited in a way. I didn't specify exactly in what way they will be inherited. Let me just mention very briefly. What you will learn later on is called subcontracting. At a runtime, for this particular feature here, for the precondition here, it's going to check pre number 2 or means disjunction. We're going to review a little bit of logic when we talk about subcontracting, but I'll just mention quickly. Precondition number 2 or precondition number 1, disjunction. And when you check the postcondition for that, it's going to be postcondition number 2 and postcondition number 1. So this is conjunction. Exactly why? One case, it should be disjunction. The other case should be conjunction. There's some reasoning behind, which I will explain a little bit later. Hopefully that answers your question briefly.
Yeah,
wow. Okay, anyway, so my point is, we definitely inherit code in the inheritance. We also inherit contracts. Okay, but exactly how, I will talk a little bit more detail later. Let me go back here. Okay, so we talk about abstractly how the expectation can be different. Let's do one example right away, right? So I'm going to make this page empty for you so you can do some exercise. So when you check out the notes for today. That one you can try to fill in the ancestor, expectation, and descendants, etc. Right? Let's do some example that's going to be directly relevant to our running example today. I'll do another one together with you. Let's say we have this particular smartphone hierarchy, right? From before. Okay, you have also a copy with yourself. Let's say we got 3 classes. The green one is going to be the smartphone, and the blue one is going to be the green one here, and the blue one is Samsung over here. And also we got the red one, which is iPhone 11 Pro. Basically, I want to show to you exactly how you can think about expectation and see which one, which class, green, red, or blue, actually got the most or the widest expectation. Okay? Let's see, okay? You might have an answer already abstractly, but I would say we'll do one example carefully, because that's kind of the exercise you have to do in order to understand the design pattern later. Okay, let's see that. The green one over here, can you tell me what are the ancestors for the green one? Ancestor. Any, I agree, but let's not worry about any. Usually when we talk about, we don't talk about any, usually, unless we really have to. If we say we don't have any, should we include any other class as the ancestor for smartphone? Smartphone itself, exactly. Okay, I'm going to put it here. Smartphone. Remember, a class is at the same time its ancestor and also descendants. Don't forget. Okay. Go ahead. I think, okay, the question was why a class is at the same time its ancestor and descendants. It's simply because we're going to define some rules for you to justify whether a particular assignment in the context of inheritance will work. And to make that rule work, we have to follow this definition. Just some definition. Yeah. Okay. So now, what about expectation for smartphone? How many features can I call potentially on smartphone? How many? 2. Good. Dial and surf web. I'll put it here. Dial and surf web. Okay, and what about descendants in this case? What are the descendants for smartphone? We'll put it another way. What classes will not be included in this case? Nothing. Everything will be included because smartphone happens to be the root of this hierarchy, including itself and also all its children. Children's children should all be included. So what I will do is, over here I'll say all classes in the hierarchy. In the hierarchy. Okay, hopefully the first one is not too bad, right? Let's take a look at the second one. Let's say Samsung. Okay, Samsung over here, okay? Let me just make a little bit room over here so you can still see the feature, okay? So now, what would be the ancestor for Samsung? Be precise. How many classes are there for the ancestor for Samsung? I heard 3. Everybody agree? Samsung itself, Samsung itself, its parents, parents, all the way to the root. So that would be, I would say Samsung over here. We got Android, and also we got smartphone. That's ancestor. What about expectation? Now you got to do a little bit of a calculation in your mind, right? How many features are there that can be called upon any variable that's declared to be of type Samsung? How many? 1, 2, 3, 4. 4 actually, right? On top, it's not a feature. Yes, you can. Let me see this. First of all, you can see, starting from the root, right? You can see dial and also surf web, and also, yeah, dial and surf web. Surf web already counted once, so we don't need to count it twice. And also Skype is some new feature here. Also side sync, right? So we got 4 features in total. Okay, let me put it here. So it will be dial, it will be surf web, it will be Skype, it will be side sync. And I can give you one note remark right away. You can see for its parents, for its ancestor, which is smartphone, it has exactly some common expectation over here, right? You can see that's common. What if I didn't highlight like Skype and side sync is something additionally I can expect on the Samsung as opposed to a smartphone. Okay, think about this kind of issue here. And what about descendants? How many descendants we have? 4, Samsung. 3, good, very good. So now you can see Samsung and also this guy and this guy, right? Okay, you can fill it in. Okay, 3 classes, okay? Okay, finally, we want to do another one, which is another branch. The reason I'm doing this is for you to figure out if you got siblings or cousins in the hierarchy. For example, you can see iPhone 11 Pro in the red, also Samsung in the blue. They are not really like directly either ancestor or descendants relationship. They are more like cousins, right? In that case, that means if they have some common ancestor, in this case, smartphone, you will see the expectation will overlap, which is exactly the expectation of their common ancestor, number 1. Number 2, there will be some other features which you can call in iPhone 11 Pro, but not the other, and vice versa, right? That's kind of the remark I want to make, okay? I think this example is pretty nice, simple enough, but that illustrates all the important things you should know about inheritance. Let me write it down for completeness. So here, ancestor for Samsung, oh, sorry, not Samsung. I mean iPhone 11 Pro. Would you agree 3 classes? Okay, so that would be iPhone 11 Pro, its parents, iOS, its parents, all the way to the root, which will be smartphone. And now notice one thing here. You can see the only thing, these 2 classes, and they are cousins, as I said, right? The only thing that's in common is smartphone. That means the pink one I just highlight are their common ancestor. Okay? Let me put it down here. So what I meant was, for this particular class, it is the common ancestor. How about lowest common ancestor of iPhone 11 Pro and also Samsung over here, okay? The lowest common ancestor means what they will overlap in their expectation will be exactly what you can expect on this lowest common ancestor. Let's verify that, okay? Let's complete the final step. So now, if I want to figure out what are the expectations for the iPhone 11 Pro, for sure, you're going to get dial and surf web for sure, right? Starting from the root. So you got dial and also surf web. And then, would you agree, we also got FaceTime over here, right? I would say FaceTime. And also, you got something very specific to this one, which is quick take. And now, let me be consistent here. So now you can see these are the common expectation, right? One more remark to make. If I have these 2 variables, let's say, I have object number 1, also object number 2. Let's say object number 1 is of this type, Samsung. Object number 2 is of this type, iPhone 11 Pro. Okay, given these two declarations, so that means that'll be the basis for compiler to make any analysis, right? If I try the following two assignments, number 1 and number 2. Object 1 is assigned to object 2. Object 2 is assigned to object 1. My question is, which one should be invalid? 1, 2, or neither? And a hint for you. In this case, you may want to look at their set of expectation. If one is a subset of another, then one way might work. If the set of expectation are exactly the same, you can do both ways. If they are not really overlapping potentially, you cannot do either way. So would you agree in this case, which one should be valid? Can 1 be valid? Not really, right? Can 2 be valid? No, right? So the rule, as we'll see later, I'm going to make a conclusion in just a moment, okay? So now, both of these will just be invalid. None of them will compile, okay? When you actually download the source code for the inheritance, which I made available in the lecture site, I got some classes over there for you to try, okay? You can try such stuff just to make yourself familiar. And whatever you pick up from this particular language, it also applies to any OOP, right? We are not doing anything specific to iPhone, no, okay? So now, no, because you can see there's something that's specific to this particular Samsung. There's also something that's specific to the iPhone 11 Pro. So you just cannot assign to each other. Okay. So now let me make a rule right away. Right. You will see the more formal writing in the slides. I'll let you read them. I want to give you intuition in the lecture. Okay. In general, if you have such assignments, object number 1 is assigned to object number 2. Okay, just variables. And the question is, does it compile? Simple question. Okay? Assuming that we have some inheritance hierarchy, assuming that. Whether this should compile depends only on the static types for the object 1 and object 2, how they were declared. Okay, I'll give you an example here. Let's say we want to figure out what's the static type of object number 1. We want to figure out what's the static type for object number 2. And then we want to see whether one class is the descendant class of another. That's basically what we're going to do. Well, before I do that, let me say this. Let's say we have some hierarchy for the classes, let's say, right? You may have, the hierarchy can be arbitrarily complicated, right? Something like that, right? And etc. So now, let's say this. If the let's say I put the more precise declaration here. Let's say I declare object number 1 to be class A. I declare object number 2 to be of class B. Okay? And then, of course, you may have arbitrarily complicated subtree over here, right? Hopefully you can see what I'm trying to draw here. Okay? It's a very complicated hierarchy. Now, static type for object number 1 is A. Static type for object number 2 is B. Okay? Now, what you really want to decide is whether B's expectation somehow is at least as many as the expectation on A. Okay? Let me put it down here. Expectation of the static type of object number 2, which is B, should be at least as wide or many, okay? Doesn't matter. As the expectation of A. For example, if I have, let's say, B over here, let me make it a little bit more. Okay, let's say B here. Let's say A is let me just make it more. Okay, let's say B is here, somewhere here. B is here, and also A is over here, right? You can see where the position is, right? In this case, do you think the assignment should be okay? That should be okay, right? You can see indeed, the right-hand side static type, which is B, is definitely a descendant of A, right? That's actually how you look at that. What's the rationale over here? The rationale is, once this assignment was actually executed, you know that whatever we can call on object number 1 will be based on the expectation of A. In order not to crash anything at the runtime, you want to make sure whatever that can be supported by B is at least as many. So that's why it should be a descendant class, okay? Because you know that the lower the class is, the more expectation you can have, just at least as many. That's a very critical insight into it, okay? Now, let me ask you this. Let me change the example slightly. If I have over here, you know what? Let me just leave it clean. Okay, we'll see more examples. Okay, so guys, is the most important rule for you to know about polymorphic assignments, right? You want to make sure the right-hand side, figure out the static type from the declaration. It should be a descendant class of the static type on the left-hand side. And we're going to see lots of occasions like this. Okay, after this, let's see what else. So now let's look at this very quickly. Okay, let me just look at this slide. I can tell you which part you should really read, which I already covered. Okay, we talk about expectation over here, right? Everything has been covered. Okay, you can look at the slides for more formal writing there. The lower the class is, the more code, the more expectation you may have. Okay, and then everything has been said here, and then read this very carefully because especially the last one. A descending class contains at least as many features or expectation as an ancestor class. That's why you can actually use it on the right-hand side, okay? But not vice versa. Okay? And this slide here basically tells you every time you have an assignment, V1 is assigned to V2. If you do have some inheritance hierarchy in the context, that's how you judge, right? Exactly what we said. You want to see what's the static type for V2 and what's the static type for V1, and trying to see if one is descending class of another. Don't get the direction wrong. Okay. Any question about this? Okay. I believe you learned something similar to this maybe in 2030, maybe a few years ago, maybe some turns ago. Any questions that needs further clarification? Okay, everybody's okay. Yes?
So when you assign the object 2 to object 1,
Mm-hmm.
essentially object 2 loses its unique feature because it just only matches the features which is the same as object 1.
When you do, okay, let me try to answer your question using one example here. You're basically saying this. Let's say we have object number 1 that's pointing to some objects over here, right? Dynamic type is not important in this case, right? And object number 2 is also pointing to just another object, right? Let's say the declared type. Object number 1, it was declared to be of type, let's say C1. And object number 2 was declared to be of type C2, okay? Let's say. And now, in order for object number 1, let's do an assignment, right, in the middle. In order for object number 1 is assigned to object number 2. In order for this assignment to be valid, what's the rule? Okay, let me write it down. The static type is C2, right? For object 2 is C2. C2 should be a descendant of C1. And C1 is exactly a static type for object number 1. Okay, let me explain again why. Okay, it's really important. So now if you think about the class hierarchy here, it's like a tree, right? So now that means over here, C2 should be strictly lower than C1 in the hierarchy because C2 is guaranteed to have as many expectations as C1, right? And go a little bit more to that. And this one can link it to the intuition I talked about for polymorphism. Let's say after this particular after this particular assignment is executed, so that means object number 1 is not going to point to this object anymore, right? It's now going to point to wherever object 2 is pointing to, right? So now, question for you. What can we call on object number 1? Depends on which class. C1 or C2? C1, because object 1 was declared to be of type C1. So whatever, even after the assignments, what we can call on object number 1 corresponds to the static type of object number 1, which is C1. So that is to say, in order for this particular expectation to be fulfilled, right, which will be C1, we want to make sure the object over here can support at least as many as C1. In that case, if C2 happen to be a descendant class of C1, it's guaranteed to have at least as many. Right? That's kind of the rationale here. We don't do a formal proof, but it's more like an intuition. Say that again. I don't quite follow you. Yes, exactly. We're thinking this way. Given that this is a relative position of C1 and C2 in the hierarchy, right? It's guaranteed in this way. You can think about the expectation of C2, if that's this particular set of features. It's guaranteed the expectation for C1 will be fewer, right? Expectation of C1. So when you try to call something on object number 1 after this particular assignment, whatever you can call on object number 1 is actually in this particular pink set. And given that object number 2 originally comes from C2, which is guaranteed to support as many as the pink one. So that's why it's valid. If you go the other way, it's not going to be valid. But we did it also exercise before. Okay? Yes?
So if C2 overrides one of the methods, we'll call that overridden method, right?
Yes, exactly. But what you're talking about is more like a runtime behavior. So that'll be subject to the dynamic binding, which we'll speak about. Yeah. So now we only talk about compilation. Right? All right. Let's go on a little bit. Okay, everything's been set. And now, this is the most important rule for you to, not to memorize, but if you really understand the intuition, you can easily reproduce this rule. It's simply saying if you got an assignment, you want to make sure the right-hand side static type is descendant class of the static type on the left-hand side. Okay, that's what it says. If you go the other way, it's not safe because you might crash the program. Okay, so I don't need to read off the slides, right? It's going to be a waste of time, but read the slides after the class. Okay, I already gave you all the intuition. So what we want to talk about is a very brief review on static type versus dynamic type before we talk about casting in just a moment. Okay, and you may declare static type in different way. Let me just reproduce the example over here. Okay, static type really tells you about expectation. Again, let me emphasize. And let's use two examples to illustrate. Either we can use the hierarchy for the student management system, or we can use the smartphone. Okay, let's use two examples over here. Okay, now every time you want to declare your variable to be of a particular type, right? You always have to face some design choice. Either go for one class that's higher or one class that's lower in the hierarchy. Which one should you choose? It's really up to what you need, but you should know the consequence of choosing one or the other, right? Can anybody tell me, and I'm going to tell you the answer for sure, let's say I got design number 1 to say I declare Jim to be of type students, versus if I declare Jim to be of type resident students. Apparently, it's more like a choice. You cannot declare Jim to be of the same of two types at the same time. What would be the different consequences of doing one or the other? What would be the difference, really, in terms of expectation? Justin? Yeah, exactly. Can you, okay, so here you can say, this one here definitely got more expectation, simply because it is in a lower position with respect to students, right? So now if you say over here, the consequence will be, you can say Jim dot all the classes over here. Remember the table we did last time, right? So this one is more like a review. You can say register, tuition, name, and courses, and that's it. If you try to say Jim dot premium rates, it's not going to compile because it's simply not within the expectation for students. On the other hand, for design choice number 2, you can say gym.register tuition name and courses plus all the new features that's declared over here, right? So it can be premium rates and also set premium rates. So these are all fine. You can see the consequence will be different. So which one to choose is completely up to you. Okay? But you should know what the consequences are. Okay? Let's do something a little bit different. But we did this already last time. How about here? So now we are referring to a different hierarchy, but the same principle applies. Design number 1, design number 2. What will be the difference here? Which design is going to give you more expectation? Design number 2, would you agree? All right? Simply because, okay, let me be a little bit briefer since hopefully everybody got it. iOS is over here. Smartphone is here. That's higher, right? So which means iOS, the lower one, has more expectation. So specifically, if I now say my phone dot FaceTime, for example, this will be considered as okay in the second design, right? On the other hand, on the first design, if I say my phone dot FaceTime, it would not be okay because statically speaking, it's smartphone, which does not support the FaceTime, right? So this is not okay, right? Any question about static type? It's quite an easy concept in some way. You want to be very clear about whenever if the question is only about what would be the consequence at the compile time, you only consider static type. But later on, we're going to talk about runtime behavior, in which case we talk about dynamic type as well. So here, we say design number 1, we declare and my phone to be of type smartphone. So that's one possibility. Or I can say design number 2, I declare my phone to be of type iOS. They belong to the same hierarchy, but one is higher, the other one is lower. So here we are just talking about what might be the consequence of declaring one but not the other. Okay. Yeah.
So can we say that each cluster can send a class and existing class for itself?
Say that again, sorry.
Can we say that each class has a descendant class and existing class for itself?
Exactly. So what you just said was, is each class its ancestor and descendant class at the same time? Yes, indeed. For our definition, it's important to realize. Yeah. So that is why, in some way, thinking this way, right? That's also something you did. But now, according to our definition, right? Let's say if I only got, let's say, class A alone. Let's say there's only a single class in your projects, just called class A. Implicitly, you can think about class A is like an inheritance hierarchy with just one single class, right? There's just no inherit, just one single class. If I say object number 1 of type A, object number 2 of type A. Now, if I say object 1 is assigned to object 2, quite obvious is this should be allowed. But why? Because A is a descendant class of itself, right? Just a confirmation, all right? Okay, so now we talk about some tracing quickly. Okay, what I'm going to tell you is basically on the slides all the way until. Okay, so here just confirming what we just said about expectation. Okay, I don't need to repeat. And also we talk about dynamic type, which is about what the type is at the runtime, and you might change that as often as you like. I'm going to use one example. So all the way until I will show you exactly. Okay, I'm not skipping anything. I'm going to do it on the iPad to be more efficient. Okay. I would say all the way until here before I give the definition. Okay, I'll illustrate on the iPad. Right? You can also read the slides later. Let's say we have this particular example. Let's go back to the student management system, which is simpler. Okay. Again, let's say we have our students at the top, and also we have resident students, and also we have non-resident students. Okay, very quickly. Okay? All I want to know is about, from line number 10 to line number 13, which one of them should compile. That's all I want to know. Okay? Right. Let's do one line at a time. Should line number 10 compile? Yes? Okay, so now I'll just do one example together with you. You can do the rest. Okay? You the way to justify, of course, you're quite familiar with this example. If I give you a different one, hopefully you also know how, right? This is the process. What you should do is figure out the static type for the right-hand side. In this case, the static type is simply, you can see RS is over here, right? Is resident students. Let me be clear here. So RS is the static type for the right-hand side, okay? What about the left-hand side? For the left-hand side over here, the static type is, you can see for Jin, is actually students. So that means it is students. And now you can see that over here, that's the static type for the left-hand side, right? You can see the blue is a descendant class of the pink. So that's why it should compile. If you got it the other way, it shouldn't compile. That's kind of the process you have to adopt, right? We'll see many scenarios like this later, okay? Okay, you will see in the slides there are other examples. I'll let you do it by yourself, right? So these are just different exercises over here, okay? I'll leave them to you, okay? Because they are not that hard. I want to do a little bit more emphasis on the casting. Okay, and this is another more or less like a repetition quickly, just about if you got code like this, right? How can you predict the behavior? Okay, this is more or less the example of dynamic binding that we talked about last time. Okay, let me just mention very quickly. Okay, basically what you have is you have Jin over here. You can see over here the students is the static type. Okay, and then so these are the two lines where we try to create different attachments or bindings for students. Okay, so now let me give you a rule very quickly over here. You can also refer to that on the slides. Let's say I have object number 1 of type A. Okay, class A, static type. And then somewhere in my code, I'm trying to say creates object 1, assuming that it's a make feature in the class called B. Okay, let's say this. Okay, when should this particular create be compilable? Should A be a descendants class of B? Or should B be a descendant class of A? Again, the way to judge is by thinking about expectation. Right? I'm not trying to be tricky here. That's kind of the decision you have to make always, right? Justin, any thought?
Yeah, I would say that B has to be a descendant.
B has to be a descendant class of A. That's very good. Okay, let me, again, for those of you who may not be so clear, let me just explain one more time, if you don't mind. Okay. Let's say this. What's going to happen is this is static type, and this is going to be dynamic type. You may reassign object 1 to different dynamic type for as many times as you like. Okay? What's going to happen is like this. After this particular assignments, object number 1 is now going to point to an object over there whose dynamic type is actually B. Okay? B over here. Okay? So now, what we really want to make sure is whatever you can call on object number 1, what can you call over here? Okay, question here. As far as the compilation is concerned, I say object number 1 dot, and then I'm waiting for code completion, right? Or you can predict yourself. What are the features that's applicable after object number 1? What features can I call on object number 1? Depends on which class. Does it depend on A or does it depend on B? A, because A is a static type, okay? So here, it depends on A, which is the static type. Given that all I can invoke on object number 1 depends on its static type, which is A, I want to make sure at the runtime, whatever object I'm attaching to can support at least as many features as A. That's why B must be a descendant class of A. That's why, okay? So now let me write it down here. So A here, and then you have B over here. So A here is about the expectation of object number 1. because it's the static type. And B, being the dynamic type, can support at least as many. At least as many features with respect to A. Okay, so that's just another, only 2 rules you have to know. Okay, this is the second one. Any question about this? Okay, let me go back to the example over here. So hopefully now you will feel a little bit more comfortable here. Right? Given that students is the static type over here, students, and now we are trying to attach either resident students or we are trying to attach non-resident students, right? So now you can think about resident students or non-resident students. Okay? Notice one thing here. Okay, later when you review. So now you can see RS over here and RS. So now, what I can call on RS depends on its static type, which is resident students, right? So in that case, I can say register, and I also can say set premium rate, which is very specific to resident students. Similarly, whatever I can call on NRS, which is non-resident students, it can be either register or also set discount rate. That's also very specific, right? And one more thing to say. You can see over here, when I try to create this particular object here, how do I judge whether this particular create should be compilable? First of all, should it compile? It should, right? But why? Anybody want to try? And try to include in your answer either ancestor class or descending class. Anybody? Because in the exam, you cannot just say because it works, right? You're going to supply some reasoning, right? Anybody want to try? It's okay to be wrong. Yes? Which is resident student. Very good. Very good. Okay, so now, in this case, you can say you will compile because the resident students over here is a descendant class of the static type of RS, which happens to be just resident students. In that case, a class is simply its descendant class, so that's okay. Okay? And then we also try to do some simple reassignments over here, and then we try to call the same feature. You can see the same context objects and also the same features being called, but we're going to get different value over here. Okay? This is something we covered last time, so I'm not going to repeat. Okay? If you got uncomfortable with why you actually get different values, please speak to me after class. Right? We covered that already, so that's why I don't want to repeat. Question? You mean the, well, it's okay, they're just simply different objects, right? We're just saying 2 students who happen to have the same name. Nothing wrong with that, right? Okay, so that's about it. So let me just finally just give you a very quick definition of polymorphism. Whenever we talk about polymorphism, it's really about how many possible shapes a variable can have. For example, how many possible shapes? If I have over here, let's say, polymorphism. Right? For those of you who know about maybe Latin, I don't know. I'm just quoting that to you, right? Poly means multi, and morphism means shape. Okay? And then, if I actually have polymorphism, simply like if I have a class hierarchy like this, okay? So now, if I have a class called A over here, right? If I say object is of type A, let's say, right? I declare that. And now, polymorphism tells me the following. If I try to say creates, and then obj dot maybe make, let's say, assuming that every class has a make feature. How many possible classes can I put inside the curly brackets to make it work? How many? It depends on something, of course, so that's exactly what I want you to tell me. I will give you options. Does it depend on how many ancestors A has? Or does it depend on how many descendants A has? Descendants, right? Because remember we said over there, whatever you put over here must support at least as many expectation as A, which is static type. In that case, if you go through the ancestor path, that's the wrong way, because the higher you go, the less expectation you have, right? So that should be all the descendants under A, right? So these are all the descendants of A, right? So question mark here, any descendant class of A. Okay, it's a very general description about polymorphism. Okay, given a static type, what can you really assign at the runtime? How many possible shapes depends on how many descendants you have for A in the class hierarchy you're talking about. Okay, and then also we got dynamic binding. Dynamic binding simply tells you if you choose a particular class over there, right? Let's say this. Let's say maybe in class A, I have feature F, let's say. And then if I can choose, let's say one of the descendants over here. Let me call this maybe A, D, just descendants, right? By default, F should be inherited to this particular class, right? Okay, so now let's say if I put A, B over here as a dynamic type. Dynamic binding simply tells me the following. Okay, at the runtime, I'll talk about runtime when we execute the code. For this particular object, if I say objects.f, which version of f is it going to call? Is it going to call the f over here, or is it going to call the version of f over here? Is it going to call the version that corresponds to the dynamic type, right? Good. Okay, it's going to call this version here, okay? This one. So that's about dynamic binding. Again, that's what you learned in 2030. So if you got trouble, please speak to me. Okay? I just want to review very quickly. Dynamic binding, you can look at the slide. Let's go over that quickly. When a feature M is called on an object variable, the version of that's going to be called depends on what the dynamic type is. That's dynamic binding. Okay? Dynamic binding is also going to appear very often. Okay? So review that before next Monday, right? Before we start talking about specific design pattern. Okay? Any question about this? Right, we talked about polymorphism, dynamic binding so far. And the next topic will be cast. But before I move on, I'll take questions. Say that again, please.
What if we use the parents of the static type, but there's no expectation change?
I see what you mean. It's a very good question. What you're asking is like this. Let's say again, let's make it very simple. Good. I got class A here, and then I got class B here. Let's say I have feature F over here that's implemented. I also have feature F that's redefined. Let's say there's only a single feature in F. There's only a single feature called F in A and B. So now, let me just draw some conclusion from here, and then I see exactly what you're asking. Okay? Expectation for now on A is just F. Agree? Expectation on B also is F. They seem to be the same. I agree with you. So your conclusion might be as follows. If I say objects 1 is of type A, objects 2 is of type A, given that, can I say object 2, for example, is assigned to object 1? Oh, sorry, I meant to say B here. Beg your pardon. Okay, let me be precise over here. You can see over here, A is the pink. B here is the descendants, which is orange. And now you can see for object number 1, its static type is simply just A, and object number 2, okay, orange and pink. Hopefully that helps you, right? Okay, good. Now, let me try to mislead you a little bit, okay? It seems like this assignment here should be okay because the expectation between the pink and the orange are exactly identical, just F. However, our previous rule tells us this should not be okay because the pink is not a descending class of the orange. We got conflicting view over here. So which one should be right? That's your question, I'm pretty sure, right? Has any thought into this? Okay, yes, anything you want to say? It will be wrong. Okay, that's good. So first of all, I can tell you that it will turn out, let me just, that's exactly right. So it will turn out, this one here will be compilation error. And let me be a little bit more emphasizing here. When I say expectation, I meant the current expectation. Current expectation means I'm not accounting for future changes to my design extension, right? At the moment, it is true, there's no new feature that's added in addition to F in B. But what about in the future? I might decide one day to add a new feature to this particular subclass. I may, right? That's one of the things I'm allowed to do. In that case, if one day I say, I'm going to add also G to here. So now the expectation now become different. So there's a potential that your subclass can simply just got more expectation than the superclass. So that's why this assignment here should not be compilable in general, even if the current expectations are the same. This one might be a little bit more like a common confusion. You might think about if my current features expectation for this parent class and the subclass, if they happen to be the same, then I should be able to do such an assignment. No, that's not the case. Because the compiler, they know that later on, you might add more features to the orange. In that case, expectation become unequal. Okay, just in talk about in general case. Yes?
So let's say that object 1 type A is also going to be a compilation and say create like a curly bracket B of object A. This is also going to be compilation, right?
In this case, what you're saying is, let's say object 1, right? You're saying if I say create, you say B here, right? Dot make. Would this be okay? According to our rule, this would be okay as long as B is a descendant class of object 1's static type. Is that the case? Indeed, because B is a descendant class of A, so that's not a problem. Right? If you put the other way around, sure, whatever you like. Let's see. So now let's say I try this guy here, okay? So now if I say creates over here, and then I'd say, I want to say object 2 dot make. You're saying what if object 2 statically is B, right? If I put A here, even though their current expectations are the same, doesn't matter. All compiler checks is whether A over here is a descending class of the static type for objects. Is it? No. So it wouldn't compile. Okay. Questions? You're saying, what if A and B are siblings?
Yeah, for example,
Yeah. I would say typically a tricky case should be you actually if you got ancestor versus descendants. What you're asking was this. A here, B here, and C here. Okay? And then let's try to do a little bit differently, okay? Let's say objects 1, A, object 2, B, object C, C. Okay? Object 3, that's what I meant. Okay, we got 3 objects here. Okay, let's just try a few. If I say create over here, let's say if I got A here, object 2 dot make. And then I say create A here, object 3 dot make. And what you're asking was, if I say create let's say B here, and object 3.make. Can any one of these actually work? Can they or can they not? Again, all you look at will be the relationship between the classes, right? Okay, let's do one by one quickly. The first one, static type for object number 2 is B, which is here, right? The potential dynamic type I want to assign is A. Is A a descending class of B? No. Doesn't compile, all right? Second one. The second one here, let me use pink, right? Object number 3, the static type is C, which is here. And then the potential dynamic type I want to assign is A. Is A a descending class of C? No, right? The one you were asking, following exactly the same rule, right? So now let's do it here. Let's say this, and object number 3, the static type is C over here. Potential dynamic type I want to have is B, which is here. Is B a descending class of C? No, so it wouldn't compile, okay? For different reason, right? You can see, but always you apply the same rule, okay? All right, let's talk about casting. So everything up to the casting has been covered. Okay, I would suggest take a look after the class, right? Everything has been covered. And that's just another example, okay? The one we talked about last time. Okay, I want to talk about casting motivation. First of all, let's take a look at this particular example, and then I'll switch to iPad. Again, we'll talk about student management system. Let's say we got Jim, we got RS. And then, if I say line number 2, I want to create Jim to be of dynamic type resident students. Would you agree this is fine? Right? Resident student is a descending class of students, right? Now, I want to say RS is assigned to Jim. Should that be fine or not? Should it compile? It shouldn't compile because Jim, static type students, is not a descending class of the static type of RS, which is resident students. However, did you realize how unflexible the compiler is? Let me tell you how unflexible they are. You can see like this. Here, you can see after creating this particular object over here, that means Jin is now pointing to a resident students object, right? Which got premium rates, of course. And then we have, let's say, J. Davis over here. Okay, but don't forget, Jim statically was a student, so I'll put it over here. Statically, Jim is a student. Dynamically, Jim is a resident student, right? They might be different. However, when I try to do this particular line, RS is assigned to Jim. The reason I'm trying to do this is because I want to be able to write RS.set premium rates. Remember, for RS, it's resident students. Part of its expectation is I can set a premium rates. In this case, I should be able to set a premium rate for this object here, right? But the compiler wouldn't allow me to do that. So that's why I claim that the compiler is very unflexible. The compiler should have been smart enough to figure out what Jim is pointing to right now is a resident student. So I should be able to allow that assignment. Everybody see what the problem is? Okay, so now I have a challenge for you. If any one of you can solve this challenge here by the end of the last class, I'll give you A+ right away for the course. Okay, here's the challenge. I don't care if you fail your lab test 1. I don't care if you fail all your labs. I don't care if you fail everything. If you can solve this challenge here, I'll give you A+ right away, unconditionally. Okay, let's see what the challenge is. Now everybody is awake, right? Let's see what the challenge is. All I want you to do is define a program here. I don't mind if you're writing in IFO, writing in Java, writing in Python, doesn't matter. Okay? This program here is going to take as input some maybe IFO program or Java program, doesn't matter. Okay, some input program here, my class.e. And the class may be arbitrarily complicated, right? Using loops, using if statements, using a cross, using whatever, okay? And then you take a second input, which is a variable name. What your compiler should do is tell me a single output, which is what is the last dynamic type of variable s. Okay? Example. Well, it seems to be an easy problem because if the input goes like this, if I have s over here, you can see the last line was trying to create as a resident students. Right? In that case, the answer should be rs. If your program can return to me an answer for every arbitrarily constructed IFO program, I'll give you A+. Anybody want to try? Sounds doable, no? Actually, don't try it. For any one of you who took 2001, did you learn about something called undecidable?
Yeah.
This is a typical undecidable problem, which means there doesn't exist any program which can do it. Right? For example, I can trick you by saying my input goes like this. Already in Java, so it may be a little bit more native to you. What if my program goes like this? I got something over here, and then I simply say while, and then I'll put some arbitrarily complicated condition over here. And then over there, I would say, maybe after this, I would say maybe S is assigned to new resident students. Now, can your program tell me right away the answer should be RS? Not necessarily, right? Because you have no idea whether we can even get there. Maybe your program never terminates. Right? Let me just say one more thing. The best your program can do is by saying, I'm going to simulate this at the runtime. And then to see, maybe eventually I can actually terminate from this loop, and then I can execute this line if I could. So that means the answer should be RS. But the problem is, what if this answer here never return false? In that case, never return false. That means it never exit from the loop. In that case, you will never get the answer, right? So it's an undecidable problem. Jordan.
You can also just write a program that runs your program that figures out the type and then change the type if it got the right one.
No, it wouldn't work because you have no idea whether you'll reach the last line or not.
So what I'm saying is like your like program that figures out the type of the variable.
You mean the dynamic type?
Yeah. So you could write a program that runs that program, and if it's saying it's going to get a string, then you change it to something.
Maybe write it to me, and then I will take a look.
No. So I'm saying
why this wouldn't be possible? Yes. Yeah.
Work.
Anyway, exactly why this wouldn't work, we don't do any formal proof in this code. I want to give you some intuition, right? I'm just saying this is a challenge nobody can solve. It's an undecidable problem. Okay. Now, why do I mention this? I want to mention this is because the reason is when we are facing scenario like this, you're wondering about why the compiler wouldn't allow me to do this, even though I know that it's pointing to some dynamic object which must support set premium rates. So that's my point. No compiler can do it. Not IFO compiler, not Java compiler, not C# compiler. No compiler can do it. Okay? The next question is, if this counts as a theoretical limitation on the compiler, then what can we do to get some imperfect solution as a programmer? Casting, exactly. So that's why we want to do casting. The problem for this, for the compiler, is the compiler believes the gym over here is restricted to whatever expectation you have for students, even though at the runtime, you can also have premium rates. What we can do as a programmer is to force the compiler to somehow change the expectation. That's what we can do. So now we're talking about changing the expectation. However, we're not exactly changing the expectation for gym per se, this variable, because we said before, once you declare gym to be of type students, you can never change it. That one still applies. What you can do instead is like this. I can say, I'm going to show you the syntax in just a moment, right? What you can do instead is to say, I can create another alias like this, gym rs. And then it's going to point to the same objects. So that's why it's called alias, right? However, I can say for this particular variable pointing to the same objects, it's going to be of expectation RS. So that can make the compiler happy. That's exactly what cast is doing. We're basically not creating a new object, we're just creating a new variable. And that new variable has more expectation that we can use. You have to do that step to make the compiler happy. Otherwise, code like this wouldn't even compile. Okay? I'm not sure if you know about this, maybe from 2030, maybe yes, maybe no, but hopefully you can think about this kind of issue, right? As a CS graduates. How do we do casting, right? That's the question, okay? The syntax for casting is actually not too bad. It's different from Java for sure, right? I'm just show you quickly, okay? One way to do it, I think that's going to be the way you can use maybe in your lab or projects later, okay? Let me just show you the syntax quickly, okay? Overall, you're going to use a check assertion. Check then, and also end. Maybe some of you already have seen this syntax already, maybe in one of the labs, maybe. If not, that's okay. We're going to show you today. So overall, it's going to be a check assertion. And the most important expression is this attach, okay? The orange one over here. Okay, first of all, the orange expression over here is going to be a Boolean expression. Either return true or return false. Okay? Either true or it's going to be false, either way. Okay? In case it is true, okay, it is going to create a variable like an alias over here. So you can think about rsgin is like an alias. Alias of gin with static type that correspond to whatever object you're trying to cast that into, which is resident students. Okay? So what we are trying to do is like this. We say rs underscore gin is now going to point to the same objects over here. However, as far as the compiler is concerned, for gin over here, remember previously we declared gin to be of static type students, right? So gin remains to be of static type students. It doesn't change ever. On the other hand, since we are now trying to cast gin into a resident students, in that case, the static type for rsgin, if succeeded, will be resident students. So now, if this cast actually succeeded, so that means now we can actually say rs is assigned to rsgin. Let me take a look. Okay, rs is assigned to rsgin. So now let's try to analyze in a similar way as before. Right? How do I know this particular assignment will compile? If you look at that, rsgin over here, the static type is exactly the type we're trying to cast that into. In that case, that would be resident students. And then, what about the static type for rs? Okay, it's actually in the previous page. I'll show you. rs is of static type resident students. And simply rs. Right? And now, is rs a descending class of rs? Yes. So now, this assignment would be okay. Contrast this particular assignment over here to over here. rs is assigned to gin, right? This one wouldn't compile because the static type doesn't match. On the other hand, this particular line will compile because now after the cast, it will match. Okay? Questions? No, gin wouldn't disappear. Gin is still there. So you can think about what we're doing in terms of cast is like this. We are just creating a new variable, rsgin. You can still refer to the gym over here. But remember, gym, the static type remains to be students. Just that. No. You can see gym is still pointing to the same objects that rsgym is pointing to. So they're pointing to the same objects. Yeah, you can still use gym if you're okay with this static type. If you want to use a static type that's more specialized, you got to use maybe rsgym. That's why you're doing the casting. Okay? Okay, Jordan.
Can you write if instead of?
Yes, that's another good question.
Okay.
I would say whether to write the if or write a check is kind of more up to you. Okay? I would say, but I'm going to use a check version. Okay? You can either say if. let's say attached. Okay, let's say resident students is RS gym. And then we do something over here, right? Maybe we do something with RS gym. Okay, so there's one possibility. There's another possibility which will be the check I talked about, right? Check attached. Yeah, bear with me. I just need one minute maybe. RS and then S RS gym. And then, okay? What would be the difference between these two constructs? You can use either one in your code, but I should know what the difference is. The difference goes like this. For this one that we talked about before, for this particular Boolean expression, if this evaluate to false, you're going to get a check assertion violation. And that corresponds more to the class cast exception that you are used to in Java. That's why I'm using this version here. On the other hand, if you try to use, let's say, this version over here, in case this particular cast actually fail, if that's really false, that simply means you simply don't do this. You just go to the next line of the code. There's no class cast exception, no check assertion violation, basically.
And you can do that for your void test too.
You can do that for your void test too, which I can speak briefly about. Okay, before Monday's lecture, review up to here for the cast, and then we're going to finish off the rest, hopefully quickly.